So here's a relatively complex circuit, and you can see it's stepped DC. There's one set of values for time less than 0. They're not all the same as for greater than 0, but they're both DC. And there are it's definitely second order. There's capacitors and inductors. And we want to find just the initial conditions at these points. So I've defined IC in concordance with passive sign convention, since capacitors, resistors, and inductors are all passive. Same thing over here for IL. And our goal is to find the following quantities. We want to find VC at 0 plus, voltage across the capacitor, the current through the inductor. So those are the easy ones to find. And then we'll find some difficult ones to find. The voltage across that 4 ohm resistor at 0 plus, and the voltage across the inductor at 0 plus. Remember, it's easy to find current through the inductor, but not voltage. And if we find these things without being primed, we also want to find all of them primed as well. I'm going to give myself a little more room for this. Now, if you are solving an actual circuit, you would not be solving for all 8 of these things. If you were asked to find the voltage across the inductor, you would only find these 2, just the voltage across the inductor at time 0 and its prime. I'm going to rewrite that a little bit more clearly there. Similarly, if you were asked to find the voltage across the 4 ohm resistor, the only ones that you would find would be these 2. I'm going to walk through all 8 in this example, only because I think that this is the hardest part of solving second order equations. So if you see how to solve for any voltage or current in the circuit and its derivative, then you'll feel comfortable with the hardest part of this entire test block. So to find these, using the method we discussed in the last video segment, you begin by drawing it for time less than 0. And the goal is to find the current through the inductor and the voltage across the capacitor always. And remember, in those regions, there are no U of T's, there are no switches, and capacitors and inductors go to their steady state equivalents. So capacitors go to opens and inductors to shorts. So now we'll draw it for time less than 0. In that region, this step function is not on, so it looks like a short. And I'm going to move that 4 ohm down just for a little symmetry here. Since we're in DC steady state, our 1/5 farad capacitor becomes an open. Our inductor becomes a short. That 12 amp source is still on and pumping 12 amps, 12 coulombs every second up through that wire. And now, before you start solving anything, remember what you're trying to solve for. Even though we're asked to solve for all these things in the upper right, the only thing that matters in this region are these 2 values. That's it. So these are the only 2 things we should be drawing. It's V C naught, and it's going to be I L naught. We generally use lowercase when they're functions of time and uppercase when they're DC values. So only those 2 things. Now, there's a lot of ways we can analyze this circuit. We could analyze it by doing a source transform on the right. We lose our I sub L, but we could at least simplify things to a big round mesh, one mesh. And then you could find VC naught. And then once you knew VC naught, that's the same as the voltage across the 4. So you can find the current. But it's even easier than that. I'm a big proponent for just taking a moment and look at circuits to see what's the easiest way to solve them before you jump in and start crunching numbers. And while you could do a nodal, there's only one node, and you could do a mesh, there's two meshes. I see one current source, two resistors in parallel. And so, of course, what screams out to me is a current divider. And the rule for a current divider is that the current through the resistor you want to find, I1, is going to be proportional to the source. And then in the numerator, it's your other resistor that goes in there, plus the sum of the two resistors. Now, this only works if you've got two resistors. If you've got more than two resistors, it doesn't work. The general form is I source times 1 over R1. If you want to find the current through R1, you find 1 over R1 over 1 over R1 plus 1 over R2 plus 1 over R3, and you can keep doing that forever. But this formula simplifies in the case of 2 to changing that numerator from using 1 over 1, if you're trying to find I1, to R2, the other one. Well, it's nice to use a formula that always works. 9 times out of 10, you're only going to have two resistors. And this thing always requires a calculator, whereas the one that's specific for just two resistors does not. So I would say that's in general a better way to go. So let's plug it in. We want to find I L naught. And so that's going to be equal to the source times the other over the sum of the two. And so that's going to be just 6 amps. And of course, you didn't really need to write down the current divider equation because these are both 4 ohms. So the 12, part of that current is going to go this way, and the other part of the current is going to go through that loop. Since the two resistors are identical, they're going to have to each support the exact same amount of current. And so just by inspection, it's got to divide through evenly through both. Okay, now that you know the current through the 4 ohm, the next issue is to realize that there's only 2 nodes here. We want to find VC naught. But VC naught is the same everywhere in the circuit as the voltage difference between the top node and the bottom node. And so that means VC naught is also the same as the voltage difference across this 4 ohm resistor, this 4 ohm resistor, and the current source. Now, if it was a voltage source instead of a current source, it would be trivially easy. You could read right out, but it's still pretty trivially easy because we know what IL naught is. We know that there's 6 amps running through here. And since there's 6 amps running through here, VC naught by Ohm's law has to be, VC naught by nodals has to be the same as the voltage across this 4, and the voltage across the 4 by Ohm's law has to be equal to 4 ohms times 6 amps that we just calculated above is equal to 24 volts. And so now we found the first of our initial conditions. Now, although we found 6 amps and 24 volts for time less than 0, for IL and VC specifically, those are the only 2 variables that can't change instantaneously. So if we know it's 6 amps and 24 volts for time less than 0, we also know that for time 0 plus, it can't change instantaneously. So this will also have to be 24 volts and 6 amps. Only true for VC and IL. Any other characteristic can change instantaneously.